Hi everyone. So today we'll be discussing on the topic Blossom algorithm. Yep. Let's see what the definition part says here. The Blossom algorithm finds the maximum matching in a general undirected graph. Just remember this one. What it does, it finds the maximum matching in a general undirected graph, even when the graph contains odd cycles, right? So this is one of the huge advantages. Yep. Even when the graph contains odd cycles. Yep. Again, let me read this one out loud. Just listen to this carefully. The Blossom algorithm finds the minimum matching in a general undirected graph, even when the graph contains odd cycles. Basically, it was introduced by Jack Edmonds in 1965 and is the first polynomial time algorithm solving this particular problem. Yep, it's the first polynomial time algorithm solving the problem. Just remember this. Yep, the algorithm works by shrinking the odd cycles. Yep, what it does, basically, it goes on shrinking the odd cycles that we will be seeing while writing the algorithm. You just have to remember now that the algorithm works by shrinking odd cycles called blossoms into the single nodes so that augmenting paths can be found. By shrinking the odd cycles um, into the single node, we will be finding the augmenting path. Just remember this. Yep. So this is fine, I believe. This is it for the definition part. Next, what shall we do? Let's discuss the approach as well as the algorithm. Yeah, or the algorithm. Yep. By considering an example, and then we can write the code. And if everything goes well, and if we get the desired output, we can just discuss the complexities for the code that we have written. First, as usual, let's discuss the approach or the algorithm. So let's move on with the algorithmic part. So what is our main algorithm, main goal here? To find the largest number of disjoint edges. Yeah. Uh, Through the Blossom algorithm, we should be able to find the largest number of disjoint edges such that no vertex is used more than once. Right. So we shouldn't be using the this one vertex more than once. Any vertex. Right. This is fine, I believe. So this is our main goal. Right. So that is the reason we'll be making use of the Blossom algorithm. So what's the key idea here? When an odd cycle appears, right, accordingly with the definition part, when an odd cycle appears, it blocks finding the augmenting paths. What it does, it blocks finding the augmenting paths. Yep. So this is the key idea. So we can detect an odd cycle. First thing is we should be able to detect the odd cycles. This one. Second one is nothing but we will be shrinking it into the single node. This is one of the things. What we'll do, first we'll be detecting the odd cycle, the first thing. Yeah. So after that, accordingly with the definition part itself, we have to shrink it into the single node. Detecting odd cycle, shrinking it to the single node. Then after that, we'll continue searching for the augmenting path. Yeah, that's what we will be doing. We'll continue searching for the augment paths. Finally, after finding the augment paths, we'll expand the blossom later to update the matching. So these 4 steps we have to remember at any cost. Yeah. First, detect the odd cycle, shrink it into the single node, continue searching for the augment paths after shrinking it to the single node, finally expand the blossom, right? So that we can update the matching. Yep. So this is the summarized version actually. Let's go with a step-by-step explanation by considering an example. Yep. So this is the graph. I insist you to pause the video and have a look into it. Yep. So we have the edges 1 to 2. You can clearly see it's the undirected graph, and we have the edges 1 to 2, 2 to 3, 3 to 5 as well. Yep. You can clearly see 3 to 5, 5 to 1. Yeah. 5 to 1, and finally 5 to 4. Yep. So these are the edges that we have. This is the simple example that I have considered. This is the graph. Just I insist you to pause the video and have a look into it. Next, let's move on with the first step, nothing but matching. So first, usually we'll start with a empty match. Yeah. So we don't have anything currently. So we'll be starting with the empty match. So the second step would be we have 1 to 2, right? The first edge we will be considering 1 to 2. So we have found the this is the step where we are finding the augmenting path, right? So this is fine. Yep. Matching becomes 1 to, as this is the first edge, first matching becomes 1 comma 2 itself, right? The edge we are considering is 1 comma 2. So this is fine. Next, third step will be we have to try the path. We have to try different paths, right? So see here, we can just go from 3 to 5, this one, 3 to 5, then 5 to 1, and 1 to 2. So this is fine, I believe. Yeah, it shouldn't be a cycle, so we'll not be considering 2 to 3. So we can go from 3 to 5, 5 to 1, and 1 to 2, right? So this is fine, I believe. So one thing you have to observe, we already have 1 2, right? So we already have 1 2 that has been matched. So we have the odd cycle that has been detected, right? So we will odd cycle that has been detected is nothing but 1 to 2, 3 to 5, and 5 to 1. 1 to 2. So this one, 1 to 2. Then we are going with this one, 3 to 5. You can clearly see here 1 to 2, 3 to 5, and again um, 3 to 5 and 5 to 1. This forms a cycle actually. Yep, this forms a cycle. Yep, you can clearly see here, right? So this is nothing but the blossom. We call this one as blossom. Yeah. So then what we'll do accordingly with the algorithm, after finding the blossom, we have to shrink the blossom or expand. Before expanding, we have to shrink, right? So we have to shrink the blossom. So what we'll do, we will collapse 1 2 3 5 to B. So one thing here is nothing but we will be shrinking the this one blossom, and we have to collapse 1 2 3 5 to B, right? So you can just look at the graph here, 1 2 3 5 this part, 1 2 this part, and 3 5 to nothing but B, right? B nothing but it consists of the 4. So to this one, to this part, yeah, we will be collapsing 1 2 3 5 to B actually. So graph becomes B to 4, right? Nothing but 5 to 4, right? So we are seeing 5 to 4, that not 5 to 4, sorry, 1 2 3 5 to B. So graph becomes B4, right? So this is fine. So next what we have to do, we have to find the augmenting path, right? Accordingly with the algo, we have to find the this one augmenting path. So we have B to 4, matching becomes 5 and 4. Yeah, I said it correct itself, so I got confused. So this one, B to 4 nothing but in the place of B we'll be going with a 5. This will be 5 to 4 actually. Yep. After expanding the blossom, we get 1, 2, and 4, 5. Right. So we have shrink 1, 2 this way, 1, 2, 3, 5 to B, nothing but 4. Right. So after expanding the blossom, we get 1 2, 1 2 remains same, and instead of the 3 5, we will be going with a 4 5, right? So as we need to this one, ignore the cycles actually, right? So we this is the maximum matching actually. We got the maximum matching in this form particularly. We got here 1 2 as well as 4 5. Yep. So this is fine, I believe. The two after expanding the blossom, right? So this is fine. So this is the output that we need to get actually accordingly, and we have if everything goes right, this is the output actually. Yeah. So this is fine, I believe. This is it for the algo. Yep. We have I have showed you single step, right? Every step correctly by considering this example actually, right? So we get this forms a cycle 1 2 3 5 as well as the 5 1. This forms the cycle. So what we do, we'll assign that one to the B, nothing but 1 2 3 5 to B, so that we can go with a B4, right? So B4 is nothing but B. We have got 5 here, right? So 5 and 4, we got the extra edge here, nothing but 5 and 4. So after expanding the blossom, we get 1, 2, and 4, 5 respectively. So this is it for the algorithm. It's as simple as that. Yep. Now, mm, yep, we are done with the algorithm part. So I hope the algorithm part is completely clear. Let's try to articulate the same thing in the form of code. Yep. So if everything goes well and if we get the desired output, later we can discuss the complexities. First, let's try to articulate the same thing, whatever we have discussed, the approach or the algorithm part. So let's articulate the same thing in the form of code. Let's do that quickly. So let's do one thing. Let's continue with the code. So first thing, so we'll be making use of the input output package. I'll just go with input java.io.star, and also we'll be making use of different utilities. For that I'll be making use of the utility package. Yeah, so this is fine. The first step would be, so here let's do one thing. So let's go with the main class that contains the algorithm implementation, right? So this one itself, blossom algorithm. So first thing, let's go with the number of vertices we went with is this one, 6, right? So I'll just go with basically from 0 to 5 in the example, right? So I'll just go with static int n equals 6. Yeah, this is fine. The next part is, let's go with the adjacency matrix representing the graph. Yeah, I'll just go with a static here int G equals new int of 10 and 10 respectively. Yep, so this is fine. The next part, let me go with static here. In let's do one thing. I'll just go with a match. Yeah, so this one will be new int of size 10. Yep. So this is nothing but this stores the vertex match with a vertex I. Yep. So next, no need of space here. We are just mentioning this one, right? So this is fine. So let's go with a parent array. Basically, we are making use of the parent array to reconstruct the augmenting path during the BFS. We'll be making use of the BFS, and BFS uses Q, right? So these things we'll be making use of. So I'll just go with static here. In. So let me go with the parent. So this one will be again the same thing. Yeah, mention the size. And next, let me go with the variable used actually here. So 1 second. So let me go with Boolean here. Used equals the same thing. Size remains same. And now I'll just go with these are the global variables I wanted to go with. 5 global variables, right? You can clearly see. And next, let me go with the method find path. So we need to find the augmenting path, right? For that, let's write the method find path. So I'll just go with static here. This is fine. This is of the type Boolean, right? So yeah, so Boolean. So let me go with find path, and I'll just go with a parameter. So we need the root as parameter. So I'll consider root as parameter. So this is fine. Next, so basically what does this method do? This method will try to find the augmenting path starting from the unmatched vertex root. So we have to reset the parent array. So every vertex initially has no parent, right? So for that, let's make use of the arrays.fill. Yeah. So I'll just go with what happened to this one. Yep. Arrays.fill. So let me pass the parent here. Yep. I'll just go with the parent as well as -1. So after resetting the parent array, so we have to reset the visited array before the BFS as well. The same thing, similar thing actually, arrays.fill. So I'll just go with, let me go with used, and let me initialize everything with a Boolean value false. So this is fine, I believe. And we will be making use of the BFS as I've said, and BFS uses Q. We have to make use of the Q, right? So I'll just go with the Q. So I'll just go with, let me go with the integer as we are dealing with the integers. And I'll just go with the Q. So let me make use of you can just make use of the array or linked list. I'll just go with the linked list. So this is fine. So after successfully creating the BFS queue, we have to push the starting vertex into the BFS queue, if you know the BFS, right? So I'll just go with the q.add of root. Yep, so this is fine. Next, what shall we do? We have to mark the root as visited, right? So I'll just go with used here, used of root. So let me assign this one to the Boolean value true. So this is fine. Next, let's go with a standardized this one. What do we call? BFS loop, nothing but while loop. While queue is not empty, then what shall we do? First, we have to remove the front vertex from the queue and explore its neighbor. Usually, we'll be making use of the poll operation, right? So if you know the this one BFS algorithm, so it's very easy to implement if you know BFS pretty well. So I'll just go with q.poll. So this is fine. The next step, let's check all the possible vertices to see if the edge exists with the V. So I'll just go with a for loop here. So I'll just go with for u equals 1, u less than or equal to 5, and let me increment the u. So within the for loop, the first thing is, let's go with the two conditions. One is edge between u. If we will be checking if the edge exists between u and v, and we will also check if we can avoid exploring the direct matched edge again. These two things. Yep. So I'll just go with simple if condition here. If g of vertex v and u, yeah, so this is fine. If it is equal to 1, and we have to check to avoid exploring the direct match edge again, right? So I'll just go with the match. We have already considered variable match of v. If it is not equal to u, then let me write the simple if condition, one more if condition here. So if the neighbor u is unmatched, then we have found an augmenting path, right? So this one, neighbor u to the v. So if this particular this thing, what do we call, neighbor u is unmatched, then we have found an augmenting path, right? So I'll just go with if match of u, suppose unmatched in the sense we will be going with a 0. If it is unmatched, then we have found the augmenting path, right? So I'll just go with match of u. Let me assign this one to the v. It's as simple as that. Now we have to match the v with u, right? So matching is symmetric here. So I'll just go with match of v. Let me assign this one to u. One, yeah. This is fine. It's simple. Finally, augmenting path has been found. So we have to return the success. In our case, as we have went with a Boolean, so we have to return true, right? So this is fine. Yep, we are done with this part. Let me come out of this one entirely. Now, let's do one thing. If u was already matched, the vertex u that I'm speaking, if it was already matched, then we have to get the vertex that has been paired with the u. Yeah. So I can just write it in this way. If we don't have to go with, yeah, I have to go with this one variable m. So let me write here match of u, right? So if that matched vertex has not been visited yet, so if it has not been visited yet, used of I'll just give here m. So in that case, what we have to do, uh, we have to mark it as visited, record the BFS parent relationship, and finally push the matched vertex into the queue as we are making use of the BFS. Or in simple terms, to continue the BFS, we have to do this. Yep. So I'll just quickly write used of m equals to, this is fine. Then let me go with the parent of m. So this one equals v, and finally q dot add of m as well. Yep, so this is fine. We are done with this part. Yeah, let me come out of this one entirely. We don't have to, yeah, this part. Yeah, if the BFS completes without finding the augmenting path, then in that case we have to return false, right? So I'll just go with return false. Yep, so this is it for this particular method, and this is it for the algorithm as well. Yeah, so let's do one thing. 1 second. Yeah, so this is it for the algo basically, right? So I can just scroll. So we have only this one method actually, the find path to find the augmenting path. That's it. Yeah, this algorithm is simple. So example, so I'll just consider one more method, main method actually. We'll be hard coding the example, the same example that I had considered while explaining the algorithm. Yeah, or while going with the approach. Yep. So let me paste this one over here. Usually I take it from the Google or the GPT, so I'll just paste it over here. So this is fine, I believe. Yeah. So this is the example that we have considered. So as it is undirected graph, as we are dealing with the undirected graph, I have mentioned that just like this in this way. 1, 2, the same thing. Reverse 2, 1, 2, 3, 3, 2, 3, 5. This is the thing, but we have initialized this one with a 1. Assign this one to 1, right? 3, 5, 5, 3, and 5, 1, and 5, 4 respectively, right? So this is the resulting variable actually. We need the resulting variable, right? So we have to store the total number of match edges. So that is what we are finding actually. So this is one thing, and we are going with a for loop because we have to iterate over all the vertices, and we have to check if the vertex I is currently unmatched or whether it is matched. For that purpose, so I'm going with a if condition within the for loop. Finally, one more if condition here. I have called the find path method because we are attempting to find the augmenting path from the particular vertex that we have considered. Yeah, if it is successful, then we have to increase the matching size. So that is the reason I have incremented the ns variable. Finally, system out println maximum matching is nothing but we are just printing the header for the matching output. Finally, we are this part is nothing but we are iterating through the vertices again to print the matched pairs. Yeah, the last this one if condition is nothing but we are printing the each edge once by ensuring the larger vertex that is printed exactly once. Again s out because we have to print the matching pair. Yep, so this is fine, I believe. Finally, system out println. So this part, this is nothing but we are printing the total number of matched edges. Yep. So this is it for the code. Let me format the code one so that the code looks good. So this is fine. We are done with the algorithm, man. Yeah. If everything goes well, we have to get the desired output. Let me run the code. I'll just come here. Let me run the code. Hope we get the desired output. You can clearly see here maximum matching 1, 2, 3, 5, and we are getting the matching size equals 2. So we have already seen this one in the this one. What do we call? While explaining the approach or while we were discussing the algorithm part, right? So the same thing we got here, and I have written, we are showing the maximum matching size as well. So matching size is nothing but 2. You can clearly see here, right? 1, 2, and 3, 5, right? This is fine. So we are getting the desired output. Yeah, we are getting the desired output. So we are done with the algorithm part. So we are left with only one thing, nothing but discussing the complexities for the code that we have written. Let's discuss the this one. What do we call complexities very quickly? Just give me a second here. So what would be the time complexity here? Just 1 second. Yeah. What would be the time complexity here? The time complexity would lead to big O of V cube or N cube. Nodes, vertex, however you consider actually. In our case, in the code, we have considered N itself. So you can consider N cube itself. Yeah. I'll just go with the N itself, right? So this is fine. The time complexity would be big O of N cube, right? So why it is N cube? We are going with the each augmenting path search that would lead to big of E, and the blossom shrink operation would take big of V. So total searches would lead to big of V as well, right? So overall time complexity would lead to big of V into V into V, right? For these three operations, which would lead to big of V cube, or here vertex, I'll consider nodes. Big of N into N into N, nothing but it would lead to big of N cube, right? So this is the total time complexity. So what would be the space complexity here? Space complexity would lead to big of V square, right? So space complexity would lead to big of V square. So why it is big of V square? So adjacency matrix would lead to big of V square, or takes the space big of V square. Matching arrays, we are making use of the matching arrays which would take big of V, and the BFS arrays which would take big of V as well. So overall space complexity is dominated by the adjacency matrix, and it would take big of V square. So the time complexity and the space complexity for the code that we have written would lead to big of N cube, and big of instead of V, I'll just consider N here, as we have written N in within the code actually. Yep. So the time complexity and the space complexity for the code that we have written would lead to big of N cube and big of N square respectively, right? So this is it for the complexities part. Yeah, this is it for the complexities part. So we are done with the algorithm part. Yeah, let's do one thing now. Let's try to implement this particular algorithm within the within some problem, right? So let's do that.